那个尽量正面看我们用英文上课这件事情，好不好？哦，我是讲真的啊，我也不会很想用英文上课的哦。但是呢，用英文上课以后，我就觉得说啊也不错呀，哦，那个，大家用英文沟通，然后那个省得英文都忘掉了哦。那OK，4点10分就 OK。语言台 OK。Now the difference between one fundamental difference between these two courses, the course of dynamics and the course of mechanical materials, is in the course of dynamics, we only deal with rigid body. We only deal with non-parameter system. Okay. In the course of mechanical materials, we deal with flexible body. We deal with disputed parameter system. For example, let's look at this cantilever beam. All right. This is a beam. Let's say you apply a force here, and what will happen is this beam will deform. And the amount of deformation depends on two variables. One is time, the other is what? Space, right? At a different location of this beam, we have different amount of deformation. And if you go to the course or go to a textbook of mechanics and materials, it will tell you that you can describe such a phenomenon by this so-called Euler-Bernoulli beam equations, and which is a partial differential equations, which involves two independent variables, a variable of x, which is time, and a variable of x, which is a spatial variable, a variable of space. Okay. What E and I means, you can find their specification or definition here, but it's not what we want to focus here. What we want to focus is that for disputed parameter systems, the system state is disputed through space. Okay, as demonstrated by the cantilever beam examples. It is actually disputed throughout space. Spatial variations significantly impact the system behavior. This is the very reason why X now need to be an independent variable, because the deformation of the beam, as I just said, depends on X. X, the spatial variation, is something no longer can be ignored. All right? When we are dealing with disputed parameters systems. So the system dynamics are often modeled using partial differential equations, which make the modeling process much more difficult, which means dealing with disputed parameter system is typically much more complex and challenging than dealing with non-parameter systems. Okay. Now, submarine is more like a non-parameter system. It's more like a rigid body. By contrast, fishes, okay, are more like disputed parameter system. That is why the swimming pattern of bird is much more flexible than submarine. Okay, it can go around in very narrow space. Okay, it can accelerate instantaneous, and it can move its moving direction almost, I wouldn't say instantaneously, but in a very fast pace. All right. Now, similarly, a bird is more like a disputed parameter system, and our airplane is more like a rigid body. Okay, so we want to fly like a bird, not fly like an airplane. Okay, Because if you fly like a bird, you don't need an airport, right? Okay, don't need a very, very, very large distance for you to take off. All right. And now we will first now formally move into the analysis of control system. And here I want to introduce or help you to review one very important mathematical method for the analysis of control systems, which is Laplace transform. All right. Okay. Now, what do we want to use Laplace transform? Using Laplace transform can simplify the design and analysis of control systems. Laplace transform apparently is a mathematical method, and it has its own complexity. Okay, if I want to deal with control system, why don't I jump in directly? Why do I have to go indirectly by using the tool of Laplace transform? The reason why is using these mathematical methods can make the process of analysis and design of control system much more simple. Okay, much simpler. Okay, I'm sorry. Okay, let's first define what is a Laplace transform. Let's say ft is a signal of interest. If you multiply it by e to minus st and you integrate it with respect to time, this is what you will get. Let's denote it as f of x. Then f of x is what we call the Laplace transform of ft. Okay, and this is the center of the operation of Laplace transform. Okay, so eventually, in essence, what we are doing is we transform the representation of the signal from t domain, which is often what we call time domain, to x domain. Okay, because the independent variable originally is t, which is time. Now the independent variable is no longer t, but x. The question is, what the hell does x stand for? Okay, x is what we call complex frequency. Okay, all right, and we will talk about the property of complex frequency later. Okay, when you can go from t domain to x domain, okay, by using Laplace transform, and you always want to way back. Okay, if I can go from t to x, can I go from x to t? And I can do that by using inverse Fourier transform. And this is the formal definition of inverse Fourier transforms. Typically, we are only interested in Laplace transform, not inverse Laplace transforms, because you don't need to perform inverse Laplace transform by yourself. You can always look at a Laplace transform table for inverse Laplace transforms results. That is one reason. Okay. Now the other reason is that it's really not important for control system analysis, but understanding Laplace transform, by contrast, is of vital importance for the analysis and design of Laplace transform. Now let's look into the definition of Laplace transform to get a better picture of what it really is. Okay, let's starting from its lower bound and upper bound. Okay, now the lower bound is starting from actually 0 minus. Okay, right? Okay, in control, we are usually interested in the causal response of the system. What is causal response? Causal response is the part of the response due to the input applied at t larger than 0, which implies that the input is actually initialized at the times of t equal to 0, all right? Now in control, what we are interested in is the causal response, the response caused by zeros, all right? Okay, so what is, other than causal response, what is the remaining part of the response? As we shall see later, response caused by initial conditions, okay? The notation 0 minus means that we include any initial condition just before t equal to 0, which is the time of the time instant of the application of the input. All right. That's why the Laplace transform is especially useful. It naturally incorporates initial conditions into system analysis. Okay. So the reason why here what we have here is not 0, but 0 minus means that Laplace transform take initial conditions into consideration, all right? Because t equal to 0 is the time instant input stop to have an impact on the systems. And 0 minus means right before the application of the input. Okay, so if Fully describes the state of the system before the application of the input, therefore it fully describes the initial conditions. All right. Now, upper bound. Why is the upper bound an infinity? Because we chose that because we integrated infinity to capture the entire feature behavior of the signal. We don't know how long a signal will last. We simply have no idea because there are so many different kinds of signals in the world. So all we need to do is, if that is the case, I just take the integration to infinity, okay? And that will take care of every possible future behavior into account, okay? Let's spend more time on the definition of t, on the specification of t equal to 0. T equal to 0 represents the exact instant of time 0, okay? And t equal to 0 plus means t approach 0 from the positive side. It represents the immediately after t equal to 0, and it is used to define system just after input is applied, okay? It's just after an input is applied. And it excludes initial condition or the instantaneous change as t equal to 0. Okay. By contrast, t equal to 0 minus means t approaching 0 from the negative side. Here, negative versus positive. It represents the instant immediately before t equal to 0. Therefore, it includes initial condition of the system. Okay. So what really matters, what really makes a difference is the existence or the application of the input. Because once you apply the input, you create a discontinuity between the application and after the application of the input, okay? Because there is a discontinuity at t equal to 0. Therefore, we need to distinguish 0 plus and 0 minus because of discontinuity at t equal to 0. What does the discontinuity comes from? Input. If you find me repeating the same thing again, it does not mean I suffer from dementia. I'm not suffers from Alzheimer. Not yet. If I do that on purpose, okay? I repeat the same thing again, only when I think the concept is of great importance, okay? And I want you to learn it by heart. That is, I want you to memorize them, okay? To always have a good idea of what it is, okay? Okay, because it will be very, okay? Now, we talk about useful signal model, okay? The first useful signal model we introduced is unit step function. Remember that the equality sign is at t equal to 0, which implies if the unit step function is input of the system, then its inference occurs, its inference on the system begins at t equal to 0, all right? So t equal to 0, the unit step is continuous, apparently, okay? In control system, this convention is u of 0 equal to 0. So this system see the full step at the instant of the input is applied. Okay, that is exactly what we need. That much exactly was what is really happening to a control system. Mathematically, you can assume u of 0 equal to 0 or 1 or even 1/2. Mathematically, it doesn't make any difference. But in control, choosing one is a natural consistent. Okay? Now, let's go to Laplace transform. How do you determine Laplace transform? Okay, the answer is very simple, just based on the definition of Laplace transform. Let's say I want to know what is the Laplace transform of 1. So I just used this definition of Laplace transform. Let me put ft, chose ft as 1 and see what happens. Okay, if I chose ft as 1 and I perform integration, okay, I would want to go to the mathematical process one step by step. You can do it yourself. Okay, you have to do it yourself, please. Okay, you take the integration. This is what you will get, and remember that here what we have is a definite integral, which means you have to plug in the upper and lower bounds, and this is what we'll get. What I will get. Okay, so the Laplace transform 1 is actually 1 over x. Similarly, the Laplace transform of unit step function is also 1. Now remember, unit step function is not really 1. Okay, if it is 1, it means its value should look something like this. But it actually looks something like this. Okay, it only has the value of 1 when t is larger or equal to 0. So why do I have the same result, same Laplace transform? Why does the Laplace transform of unit step function is the same as Laplace transform of 1? The answer is really very easy. Because when we take the integration, the lower bound starts from 0. Okay, so it ignores what happened before t equal to 0. Okay, this is the reason why the Laplace transform of the unit step function is 1 over s. Okay, all right. Now here, what I want to do here is to let you know there is a integration technique, which is integration by parts. All right, and you should have learned in the course of calculus. All right, and this is the formula for integration by parts. Okay, this PowerPoint slide pretty much repeat the same thing. Again, this is the formula of integration by parts. And here we have an example. Okay, what is the integral of x times sin x? If you set fx equal to x, and here fx, the derivative of x is 1, and g prime of x, let's assume it is sine of x, then g of x is minus cosine of x, and you just plug these results into this so-called integration by parts formulas, and this is what you will get. Okay, The reason why I want to review this simple mathematical techniques of calculus is we will use integration by parts to determine the Laplace transform of the derivative of f. Okay, why do we want to do that? The reason we need to do that is because we are dealing with differential equations, and differential equations is made of input as and output, as well as the derivatives of input and output. All right, so we need to take care of the Laplace transform of those derivatives. Okay, let's say again, this first result is based on nothing but the definition of Laplace transform, and then by using the technique of integration by part, by assuming f prime here is nothing but a g prime of x, and e to the minus st is f of x, and I use this formula, and this is what I will get. Okay, and this is the result. This equality tells us the Laplace transform of the derivative of f prime x is actually x times over x minus f of 0. Remember that what is f of x? F of x is, of course, the Laplace transform of ft. All right? So if you look at this result, you'll see that the derivatives of f actually consists of two parts. The first is the initial value of f. This is the initial value of f. The second part, which is more important, is x times fx. All right? Remember, fx is the derivative, the Laplace transform of ft. What does that stand for? That means the derivative operation in a time domain, when the function, the signal is converted into the x domain, the differentiation operation in a time domain converted into a multiplication operation. All right? That is, if you take a derivative in a time domain, what you end up with in the s domain is you time the function with s, and that means a multiplication operation. Time domain, differentiation operation in the time domain translated into multiplication operation in the s domain, okay, which is a simpler mathematical operation. Multiplication or differentiation? Of course, multiplication, because we learn multiplication in elementary school, or before elementary school, and we learn the differentiation probably in the course of calculus, right? Okay, let's go one step further, okay? This is only the first order derivatives, but in a dynamic system, when modeling a dynamic system using differential equations, we will have to deal with higher order derivatives. So let's assume that here we need to deal with case derivative of f, and by using similar techniques, that is by using integration by parts again and again, and this is what we'll get. Again, the result consists of two parts. Let's assume k equal to 2 to help us understand what will come up, okay? Again, one part of the Laplace transform of the double derivative of f is based on the initial value of f, okay? When I say initial value, I mean values at t equal to 0. But here, not only we have to have the information of f of 0, because we are dealing with the double derivative of f prime. when it comes to initial values, we also need f prime. Okay, that's the first thing. The second thing is that we have x squared fx. Remember that here, I told you that differential operation in the time domain translate into multiplication of the x domain. This happened again, okay? Double derivatives means I have to take the differential operation twice. Therefore, if I take the derivative of f double prime, okay, or the second derivative of t, I have to multiply fx with s twice, not just once, twice, okay? Same thing, I can generalize this result to case derivative. Okay, if I take the case, what does case derivative mean in the time domain? It means I have to differentiate the function k times. Okay, now in the x domain, it means I have multiplied the function k times with s. Okay, all right, okay, all right. Please keep in mind, all right? This is a very systematical result. And if you can, please learn it by heart, because we will use this result repeatedly in the remaining part of this course. Okay, we will use this result many, many times. It would be very helpful if you can learn it by heart. I wouldn't say just memorize it, because you don't need to memorize it, because you already understand how it works, right? Okay. Now, again, the next thing I want to know is, if I know the derivative, what I'm doing here is find the Laplace transform of the derivative of f, okay? But when you come to calculus, it involves two fundamental important mathematical operations. One is differentiation, the other is integration, okay? We already dealt with differentiation. So the next natural step is take care of the integration, right? And that is exactly what we want to do. Let's say this is the integral of interest. If I take Laplace transform of this integral, this is what I will get, all right? Now, again, we need to pay special attention to the lower and upper bounds, all right? Now, let me make a revision here. This representation is actually not entirely ideal. I should replace this t by tau, okay? And tau represents the dummy variable which I used in the process of integration, okay? And t here is time, okay? It is a time variable, okay? So you can choose t to be 1 or 2 or 3 or 5. It really doesn't matter, okay? But t here is the time variable, all right? Now, what I will get is this. Okay. Again, it consists of two parts. The first part involves the past history. When I say past, I mean t, the time before t equal to 0 of ft. And the next is f of x divided by s. If you see this result, you should find it to be very interesting. Why? Because differentiation in the time domain translate into x domain become multiplication. Now, integration in the time domain, when translated into the x domain, become not multiplied, but divided by x. So this operation, this comparison really makes sense, right? Differentiation, integrations to opposite directions, to opposite operations. In the x domain, multiplication, division, two different operations, right? Two different, totally different directions, two different opposite effects, right? Okay, so it makes sense, okay? And again, I want you to learn it by heart because we will use it. Now, we don't usually, in the context of control analysis, this is not much a problem because usually f of t is 0 when t is equal to 0. Why? Because t is defined as the time instant the time instant we initialize our input. So before the application input, everything is 0. Okay? So if this is 0, this integral has to be 0. Right? All right. So here, I want to introduce another concept, which is causal signal and causal system. A signal which has 0 amplitude for all negative values of time, then the signal is known as a causal signal, right? When it comes to math, it's simply that if x of t is a causal signal, then x of t equal to 0 when for all t smaller than 0. That's it. Okay. So so if ft is a causal signal, then this part is 0. I don't need to deal with this part ever. Okay. Now that is for signal. Now what is a causal system? Causal system is known as physical system, which implies that all physical systems are causals. Or it is often referred to as non-anticipative system, which means the system does not anticipate. What does that mean? That means a system where the output depends on past and current inputs, but not the future input. It does not depend on future inputs. All physical systems, the condition of all physical systems only depends on its past and current inputs. Okay, it does not depend on input that has not yet happened, right? What is today's temperature? It depends on the time before today, yesterday, the day before yesterday. It depends on the weather condition of the past, not the future condition, weather condition, because future weather condition has not yet happened, right? So a causal system is a non-anticipative system, but non-causal systems do exist in our world because, for example, stock market. If you think stock market is a system, then stock market is a non-causal system because the price of the stock does not only depend on the past and current prices of the stock. It depends also on your imagination. Why is the price of many AI companies, of the stocks of many AI companies so high? It's not because historically those AI companies have already made a lot of money. So invest on those AI companies, we expect to make money. It's not because most of the AI companies, especially those giant AI companies, none of them is making money. They are investing heavily, but they are still losing money. But why do people still buy their stocks? And the stock price are all very high because people anticipate those companies will do very well in the future. After all, they are in the AI business, and AI business look very good to all of us. That what I say is our mindset is not reality. Okay, we will probably and very likely encounter AI bubbles in the very near future, very near future. Some people say that. If you ask me, I honestly let me give you an honest answer. The honest answer is I have absolutely no idea what is going to happen. Okay, I have absolutely no idea because, but some people think they have a very good idea. That is why they invest heavily on AI, the stocks or AI company. Okay, that is a very good, I think it's a very good example of anticipative system, non-causal system. But as you can imagine, all physical systems, all systems that us engineers have to deal with are non-anticipative and therefore causal systems. All right? Okay, this is a table, actually a very short table for Laplace transform, which means mathematically, please, by all means, don't do any Laplace transform by hand. Okay, always go to the table. The dirty work has already been taken care of, right? Why reinvent the wheels again? Okay, now so always go to the Laplace transform tables for direct transform as well as inverse transform results. Now, the next thing we want to do here, which is very, very important, is we want to use Laplace transform to help us design, analyze our control systems. Now, in this course, what is our system? Our system is this so-called nth-order linear time invariant system. Okay, it's a linear differential equation. What is the single most important property of a linear system? Superposition, superposition, superposition. Okay, I said it 3 times. I repeated it 3 times because it is very important. It is of great importance. Linear systems have to obey the rule of superposition. What is the rule of superposition? Check it out yourself, okay? Check it out yourself, okay? Please check it out yourself. Okay, now, so first of all, it's a linear differential equation. Second of all, because all these coefficients are constants, so this differential equation also represents a time invariant system. Now, the reason why it is nth order is because the highest derivative of the output is nth order, as nth derivative. That is why we have an nth order system, okay? Now, by contrast, a time-varying control system is a system in which one or more of the parameters of the system, that is these coefficients, may vary as a function of time, okay? Again, R, which appear on the right-hand side of the equality, is the input, okay? The system itself is the ordinary equation, and the output is, of course, appear on the left-hand side of the equality, and it represents the solution of these differential equations, okay? Now, here's, in this PowerPoint slides, we, again, review the result of the Laplace transform of the derivatives of signals, all right? Now, I'm sorry for the Chinese, okay, appear here, but I'll cover it, okay, with my speech. Let's consider a time invariant system, okay? Here, now this time invariant system is identical to this system. The only difference is that here we have P and Q for the coefficients. Here I have A and B, okay? Other than that, they actually represent the same thing, okay? Now, to simplify the following mathematical derivation, I will introduce a mathematical symbol, which is differential operator. A differential operator is defined as this, okay? It's denoted by D, and it represents the operation of differentiation, okay? So if this is the case, then if d equals to this, then d squared, of course, equal to double derivative. Okay. Now, when I say d squared, it's really a misleading representation because when I say d squared, it seems to me I'm saying that I have to multiply d twice. Okay, this is not the case. I cannot multiply it. Why? Because d is not a variable. D is a mathematical representation. When I say d squared, that means I perform this operation twice. Okay. Now, if this is the case, then this term can be rewritten as dny. And this term can be rewritten as d to n minus y, okay, and so forth, okay. Now, same thing happens to the right-hand side of the differential equation. So, if this is the case, after the introduction of d, this differential equation can be rewritten as this. Apparently, this representation is much more concise. Okay, well, Q of D is actually here, given here, and P of D is this. Okay, nothing fancy happened here. Okay, I has not do anything to the differential equation. Okay, all I have done is rewritten this differential equation by using a new operator. Okay, all right, okay, nothing has changed. The only change that I have made is create a more compact, concise representation for our system. Okay, now here it looked like an algebra equation because Q of D is really look like a polynomial, and P of D similarly appears like a polynomial. But let me emphasize again, they are not polynomials. If they are polynomials, D has to be variable, such as R, such as X, such as Y. But D is not a variable. D is a mathematical operation, which is differentiation. Okay, keep that in mind. However, the introduction of the differential operator simplify our representation for our linear time invariant system. All right. Now, equation 2 and 3 tell us that we assume if all the initial values, equation 2 says that here it assumes all the initial values of y are 0. Okay, which means y is 0. The value of y is 0 at t equal to 0. Similarly, the derivative, the double derivative all the way up to the higher order derivatives of y are 0, has a value of 0 at t equal to 0 minus. Same thing happens to f. Okay, remember that I just told you, if you take the Laplace transform of the case derivative of y, this is what you will get. Okay, now remember that capital Y of x is actually the Laplace transform of y of t. Okay, now if these conditions are satisfied, then I can ignore all these terms because they're all vanished. They're all vanished because all the y involved here are zeros. So let's just put it aside. And this is what I will get. Okay? Remember, this equality is only true when equation 2 has been satisfied. If this is the case, okay, then the case, if you take the r's derivative of y when translated into S domain, this means I times y of x with x r times. All right. Similarly, the case derivative of f when I converted it into the X domain via Laplace transform, this is what I will get. Okay. See how similar they are. Okay. These two representations are very similar. They actually only look it look very almost identical. Okay. Why? Okay. The only difference is this is capital Y. This normal Y, right? And this is function of time because we define it in the time domain. This is the result of the Laplace transform of Y. And therefore, its independent variable is S. Okay. Here, we take the derivative R times. Here, we times Y of X with S R times. Okay. Okay. So if this is the case, okay, now the next thing what I want to do is I want to take the Laplace transform of the entire equation by converting each element of this equation one at a time based on these two rules. Okay. And if this is what I do, then assuming that all the initial values involved are zeros, then this differential equation can be rewritten as this. All right. And I can rewrite equation 4 as equation 5 because this is nothing but Q of S. Remember, Q is divided here. All right. Now Q of X, therefore, this is nothing but the Q of X. Now, Q of X, okay, Q of D, what is the difference between them? Very simple. Difference is that Q of X is actually a real function. Its independent variable is X. Q of D, if you set it up, if you think of it as a function, then its independent variable is D, but it's actually not a function. It's actually a mathematical operations. All right, okay? But when it comes to the appearance, they look almost identical. Okay, so this is Q of X, and this is, of course, based on the definition given here, is P of X, all right? Now, this is what I will get if I take the Laplace transform of this differential equation and assuming all the initial values are zeros, then the differential equation, when converted, when transformed into the X domain, into the domain of complex frequency by using Laplace transform, this is what I get. And let me rewrite it as equation 5, okay, which again is a very compact, concise representation. We love that because as engineers, we like simplicity. We hate complexity, right? We like simplicity. We hate complexity. If whatever I do, if I can simplify the matters, that will be often my choice. Okay. Now, the next thing, what I will do here is I want to introduce a very important term, which is transfer function. The definition of transfer function is this. What is this? The definition of transfer function is the Laplace transform of the output is the ratio of the Laplace transform of the output to the Laplace transform of the input. So G of X is actually output versus input. So it gives us a very solid a very solid piece of information of the relationship between output and input. Now, based on equation 5, okay, the ratio of the Laplace transform of the output, which is y, to the Laplace transform of the input is actually P of x over Q of x, right? Because this y of x, okay, 11 o'clock. Let's take again 10 minutes break, okay?